Today I just thought we'd take a look at some general and basic motion control. I want to start off with a stepper motor, and I have here a stepper motor drive. It's called the Dragon driver. We can see some of the information here. Output 3 amps, bipolar chopper. Input can be 28 volts AC and it can be 42 volts DC. We're just going through a bridge and a big storage cap. We can have AC or DC input. We got some dip switches for our current settings and some of our I/O. We also have a slow and a fast speed potentiometer on the board, and we'll get into that in just a minute. Actually pops into this the old snap track. That's just a good way to mount it and protect the bottom of the board. I've had it for quite some time. When I was putting together a small CNC mill that I did want to use steppers on, I was actually going to use these, and I ended up using a little bit smaller, more compact to make a smaller control box. But nonetheless, I had several applications for these that worked out good, because we can either input a step and direction pulse from, say, like our Mach 3 software or some other interface, and we can also inject our own signal. We're even going to try to see if we can run it with just a cheap function generator kit a little later. But we can also use this as a standalone by jumping a few here, jumping a few of the terminals. For example, pin 1 and pin 2 here is our step in and our step out. If we jump those, we can use our internal oscillator, and we'll be doing that on the demo here. For a quick look at our motor, we got a clean damper on the end here. I've already loosened up the set screws. We'll take this off for now. So this is a Vexta 2-phase. I probably used to say 1.8 step or 1.8 degrees per step. That's a very common, so 360 degrees divided by 1.8 is a 200 step motor. That's very common. I've had these for probably 8 or 9 years, so I do have to get back familiar with them, but that's our rating, 5 volts, 1.4 amp. The 1.4 amp is important because we got to set our dip switch based on that amp rating. I'm going to put this damper back on. We'll be right back. So the damper not only dampens some of the sound and vibration out of the stepper, it also gives you a little handle here on the machine that I had it installed on. You could actually work the axis or the lead screw back and forth. I did just have this sitting on foam so it don't vibrate quite so bad. I also had one of these dampers that was cracked, so I went ahead and pulled the cover off, and it looks like we just have a weight there suspended with some gel, almost like silicone, but it's but anyway, that is our dampener. So I got my power supply hooked up to our terminals for the power of the motor. If we look through the information real quick, we'll see here we got our layout for our terminal block. We're going to make sure we look at these logic and control connections, because if we go on to this page 5, it talks a little bit about the module itself, and here's some information on the driver module that's actually mounted on the board. So don't let these numbers or terminals actually confuse you. If you see that on the sheet, it's not the actual terminal block number coming off the circuit board. So talk about our motor connections here being a 4-lead or 2-phase motor. We already got some cable coming up here, and I have them connected. If you're not familiar with stepper motors, you can ohm in between and get an ohm reading between individual motor windings from, say, 1A to 1B and 2A to 2B. I twisted these after I figured out which ones were together, but you don't even have to get your meter out. Honestly, if you leave them all separated and you put 2 of the wires together, instead of being smooth, you'll feel some hesitation, or it might even lock the rotor down, the way the magnetic field is on the little teeth of the stepper motor, the actual stator. And then if you take those loose and do the other 2, you'll feel the same thing. You'll feel that resistance. So it's pretty easy to tell which wires go to which phases, or which ones go to the same winding. So really quick here with this smaller motor here as an example, we could use a meter and go across our black and our white with a black stripe, and we get about 6.8 ohms. Of course, across any of the other one, we don't get anything. no continuity, no winding. If we go across red and white and red, we get our right at 6.8 ohms. But just to show what I was talking about earlier, I usually don't even have to use a meter. If I put two together, instead of it being smooth, hopefully you can hear that difference. Even on a small motor, you can feel the magnetic field going through the windings, where the windings actually making a closed loop. You can feel that magnetic field building up. You can do the same with the other phase together. It's a lot harder to turn it, but I think typically the larger the motor, I think it's a lot more drastic of a change. But nevertheless, it's pretty easy to do. You don't have to get your meter out typically. So if we take apart a small stepping motor, we'll see our rotor with all the permanent magnets with almost like teeth. And that's our steps. And we see our actual stator windings, and we see our A and our B, different phases, and our stator windings. And we can see that our laminations in there on the stator windings as well. Okay, back now. I have a 24 volt supply hooked up to our input, which we show on our schematic here. Right here is showing a 28 volt AC transformer. It also shows 10 to 43 volts DC here. It shows from 6 back around to 1. Sorry, that copy is a little faded. So that's how we got our motor leads connected and our power on that terminal, just as it states here. It actually shows an example here of a 4-lead motor. That's exactly what we have. Of course, our small motor is only a 4-lead motor, and we can tell here that we got a lot less torque. We probably won't get near the speeds of maximum before it actually just has too much slip to keep up. But the good thing about a 6 or 8 lead motor, you can do higher torque, lower speed by putting them in parallel. So in parallel, you'll get a higher speed and a lower speed torque. But of course, when we go into our series configuration, we'll have our lower top speed but higher low speed torque. But today's a straightforward, just 4 lead, 2 pole, so it's not going to have the most torque. We'll see how much speed we can get out of it. And now going back to our logic and control connections, we have our terminal block number here and our function. So to follow through with this really quick here, this is our pin 1 and pin 2. And we're just taking a step out and going back to our step in. We're going to do an onboard control here. And it actually tells us here we can connect the step pulse output to this terminal pulse in, or we can connect the external pulse, and we'll get to that too. We have our plus 5 volts out, which we don't have a use for at this time. Whether we're half or full step select, clockwise or counterclockwise, we can change that. It shows here back to 0 volt or ground, which is pin 10. Our enable, ground at the disable, back to 0 volts. 7 is our ground, as well as 10. And then we have a selection here where we can select our fast oscillator, or we can select our slow oscillator. So that's what I have here, is I got 2 coming off the 0 volts for 10. I have a 9, which is going to be our slow oscillator. We have an 8, which is going to be our fast, and that's actually our potentiometers for controlling our slow and our fast respectively. So it tells us here in our slow that we can get it from around 70 steps per second up to about 5,000 steps per second. And in fast, we can actually get somewhere between 1,800 and about 20,000 steps per second. That's enough talking. Let's see what it'll do. Got our 24 volts DC. I'm actually going to turn it down to just 20 volts. 20 volts is plenty. And right now this motor is already getting a little bit warm, and it is almost like a servo being in lock rotor or position lock or position control. And that's the good thing about a stepper motor. Without any other feedback closed loop device, the way it steps through 200 steps per revolution, it can be a pretty accurate way to control or to have like a tight motion control, speed regulation. Unfortunately, they don't get near as fast as servos. They don't have usually as much torque as servos typically. And without that feedback, if you get them too fast, they'll actually slip on you. You really won't, you can't tell it in your program or in your actual automation process. But other than that, if you keep the the application where you don't need a lot of torque, there's not many chances for it to skip a step. It actually works out really well. And I have used them successfully in some applications. They're just not my favorite because they can slip. And if you're going to add encoder feedback and all that, well, you might as well just use a servo. So the first thing I'm going to do is take my 0 volts and I'm going to go to pin 6, which is our enable. And that's going to take the current where my power supply was around 1 amp of holding current. Now it's just free. So it's just as free as it was before I cut the power on. So that's our pin 6. Our pin 6 enable to ground. So we're disabled. And you could actually motion the machine or whatever we're connected to here mechanically. You can do whatever you needed with it, get it in position, and once we enable it, then we're locked and it's going to hold position. Now our 8 was our fast, and then our 9 was our slow selection. If we take our 9 and we go to 0, then that's our slow speed oscillator. Which we can adjust with this slow speed pot. Hopefully you can hear that on the video. So we can go up to that fast with the slow. We just bring the meter over and go to DC volts. Keep in mind this is a pulse, but just out of curiosity, what do we have here? We can actually tell we got a pulse. We can see our output jumping around our DC volts. The way it's pulsed, and I wouldn't be surprised if it didn't show AC. Not the best way to check it, but if we really wanted to check it, we'd have to bring the scope over. We'll look at our input on the scope. So this is our low speed. And then we can also look at our just the motor output. So this is what our motor output looks like in slow, where we have the pot sitting at this time. So we remove it. It's still in our lock rotor position. Now we can go to our fast oscillator. It runs really smooth. See where we're currently at. Go ahead, there's our motor. Adjust this a little bit. There's our motor pulse output at the time. And I'll get the cursors up there like before. There we go. Let's go over and look at the oscillator step input. It's actually feeding into the driver module. There we go, that's what that looks like. We'll just take this off and get it out of the way and cut this off for now. I just wanted to mention too, while we're in high speed, you saw me in low speed put the meter across there. I did it on purpose to show you, it would show a little bit of movement. But some meters are better than others, but it's got some age on it. It's not the quickest, but you do see that our square wave pulses are so fast that if I actually try to check across the motor output leads, it's actually showing 0. So if we actually go to AC, being a true RMS meter, it's going to pick up fairly close. But I just thought I would show, because we can see on the oscilloscope here that we're actually we're getting our about 20 volts DC on our pulses. Just happening so fast that a DC meter won't pick it up. So just keep that in mind. And we could also play with this a little bit for the fast speed. We can actually go so fast that this motor don't have enough torque to keep up, and when it's pulsed around, the frequency can actually get too high to keep up, even with no mechanical load really on it. And if we go up really, really slow, the speed will get up pretty good. And actually, sometimes you can't do it because it has so little torque, but I've actually went all the way up as far as this oscillator would go. But if you were to put in a mechanical load at all, it's just steadily going, it's just singing to us with a frequency. It actually don't have any torque to get it back on track. We got to go way down. There it goes, it finally locked back in. Just a lot of slip. It can be so much slip that it won't even catch back up. If I go too fast, it'll do it as well. And one thing I failed to mention is off video I did set the current. This dip switch 2 is up, and on this sheet right here we show that for 1.4 amps we want dip switch 2 to be on, and that's how we can actually configure our current up to 2.5 amps. The 2.5 amp is actually the max output of this dragging driver. But that's just real quickly how we can use the little stepper drive to control the stepper motor. And it's not a whole lot else on board to talk about other than like it showed for full or half step. Like the full and half step. In other words, instead of putting out a full step, it can put out half steps out to the actual poles of the stepper. And if we look here, it says for your convenience, this input is wired in the parallel with the position 6 dip switch. So we could jump it, or we can just change this dip switch. So we just don't have quite as much torque with half steps. It definitely a lot back in there. So that's back to just a full step. Definitely more torque. So next I'm going to cut this off. So what I'll do is I'll disable it. Disable it. Cut this off. I'm actually going to take a loose where the step out comes back to the step in. I got a little bit nicer function generator, but this is one that came as a kit that I enjoyed years ago, just putting together yourself. If you've never done one, I really recommend it. It's a nice little function generator. It's something you do yourself. So I'm coming off here off square wave generator selector. Going to hook it into our pulse in. I'm going to tie the ground back to our power supply, so the grounds are coming. I do have it on the 1K frequency range. Enable. Okay, so we're back enabled and locked. I'm actually going to cut this on. We get just a little bit of rotation there. I'm sure I could take this on down, but I think the 1K's got enough range. Now if we crank this on up more towards the 1K, yeah, it's driving it just fine. That's our 10K range. So all the way down we jump on up to 860, about 862. You can't take that. I'm surprised it even made the 10K. That's just a quick video of the day on the Dragon driver and a small stepper motor. This is a CNC that I built out of stepper motor. It was a lot larger than the one I showed on the bench. I use stepper motors in this little small mill, and it actually works really well. My favorite CNC, I do have actual servos on. So in the next video I'll actually show a servo on the bench, and I'll just show a little bit of setup on it, a little bit of testing with it. That'll be the brush type. We'll look at it and some applications for it maybe, and do some testing on the bench. If you like this video on the stepper motor today and this Dragon driver, please like, share, and subscribe. Thanks for watching.